States has had no defense against ballistic missiles, except the threat of nuclear retaliation.
I call upon the scientific community in our country, those who gave us nuclear weapons, to turn their great talents now to the cause of mankind and world peace, to give us the means of rendering these nuclear weapons impotent and obsolete. I'm taking an important first step. I am directing a comprehensive and intensive effort to define a long-term research and development program to begin to achieve our ultimate goal of eliminating the threat posed by strategic nuclear missiles.
On March 23, 1983, President Reagan announced the research and development effort that has become the Strategic Defense Initiative, SDI. SDI is now the largest military research program the Department of Defense has ever undertaken. Aviation Week reporter Phil Klass.
In this Aviation Week and Space Technology video magazine, we will address some of the critical technologies that are to be included in the program. Intentionally, we will avoid the political issues. Instead, we're going to explore some of the more interesting and challenging technologies under investigation today, to discuss their role in the overall system, and to have an opportunity to meet, to get to know some of the scientists and technical managers who are playing a key role in those programs.
Research into ballistic missile defense began in the 1950s with Nike Zeus. By the late 60s, Nike Zeus had evolved into the Safeguard system, intended to protect the missile bases of the U.S. deterrent force. It included a multi-purpose phased array radar and computer net, and two kinds of nuclear-tipped missiles, Spartan, which intercepted above the atmosphere, and Sprint, which was meant for last-minute high-atmospheric defense. But Safeguard's radars and control centers were vulnerable to a concentrated nuclear attack. Agreement with the Soviet Union to limit ABM deployment was reached in 1972. The United States shut down its one Safeguard site in 1976, but the Soviet Union opted to maintain an ABM system around Moscow. But over the past 20 years, promising new defense technologies have emerged. Head of the Strategic Defense Initiative Organization, General James Abramson.
General Abramson, what new technologies encouraged President Reagan to issue his challenge to the scientific community to seek an effective defense against ballistic missiles?
Phil, I believe that there were about three basic trends in technology. First of all, the whole effort at fusion research in this country had produced and moved forward directed energy systems. That meant lasers, particle beams, all of those areas had moved forward dramatically. And that's a whole new area of technology. It has whole new promises and new problems. But in addition to that, we have made such tremendous progress in computers, in computer-related applications, in the development of software, that really puts us in a different condition than we were back in the early 1970s, when we had to try to create a very limited defensive system. Finally, I believe that we have made such progress in the miniaturizing of components that really does offer the possibility of cost-effective solutions that are dramatically different now and in the future than what we had a decade ago.
The dramatically different possibility is of intercepting the attacking warheads during all phases of their flight. This flight begins with the firing of the missiles themselves, the boost phase. In space, the warheads separate in free fall over the pole, the mid-course. Finally, they re-enter the atmosphere and plunge to their targets, the terminal phase, the only place 1970s technology could intercept them. Today, all phases are potentially vulnerable. None more important to a successful defense than the boost phase. Missiles in their boost phase are easy to spot, vulnerable, and every one destroyed takes with it its entire payload of warheads, as many as a dozen or more. What made boost phase defense appear attractive was the promise of a technology able to deliver a missile-killing blow over great distances at the speed of light, the high-power laser. At the White Sands Missile Range is the mid-infrared advanced chemical laser known as Miracle. It's the most powerful laser in the nation today. Originally developed for the Navy to explore fleet defense against missiles, Miracle produces a high-power beam of coherent infrared radiation. Because it's coherent, a laser beam spreads out very little when it's sent over long distances. The beam is generated by the combustion of large quantities of deuterium and fluorine. Captain Art Schrader.
The beam that is generated in the laser below us here is then routed through an optical system, squared up, various diagnostic measurements are made, and ultimately the beam comes up through the tower behind us and to the Sea-Light Beam Director. Miracle first lased here at the High Energy Laser System Test Facility in the summer of 1984. We went through a characterization period which culminated eventually in the tests last September that were done to support the SDI program. This test series included the Titan booster that for the first time put this level of power of a high-energy laser on a full-scale target.
The control center for Miracle is in a separate building. Director of the High Energy Laser Systems Test Facility at White Sands, Dr. John Davies.
The purpose of the Titan 1B experiment was to deposit a certain amount of laser energy on the surface of the missile and see what kind of effect that would have. And the missile itself was loaded in such a way that it simulated the static forces it would feel during the flight if it were engaged while in the boost phase. The principal result of the experiment was that the laser fluence levels that were deposited on the missile body caused the missile to destruct.
A major task of the Miracle laser today is to find out how much energy it takes to cause lethal damage to a missile, even one that's been hardened to withstand laser attack.
And in this particular test series, we deposited laser energy on a sequence of material coupons that represent materials of interest not only to establish vulnerability of systems that are constructed of these materials, but also to evaluate new materials as possible hardening candidates.
The beam director is now being integrated with the laser itself so that the system can be tested against moving targets. When Miracle was designed, the goal was high power, about 2 megawatts. Size and complexity were unimportant. For the newer Alpha laser, also developed by TRW, the goal is generating high power, but by a system of compact modules able to be lifted to orbit. Early SDI plans anticipated that space-based chemical lasers like Alpha would play a key role in attacking missiles in the boost phase. Today, their role is more questionable. SDI Deputy Director for Technology, Dr. Louis Marquet.
The difficulty with the chemical lasers that we are aware of now, and I'm talking primarily about the hydrogen fluoride type of chemical laser embodied in the Alpha program, the primary difficulty is its wavelength is relatively long. Alpha, an HF laser, operates at about the 2.5 to 2.7 micron region. Ideally, we would like to have a laser, a chemical laser in space that operated at perhaps a half a micron or smaller, so that we could use small optics. In other words, the size of the wavelength drives the size of the optics. And for space-based applications, you'd like to keep your system as small as possible.
Initially, your organization seemed to favor basing high-energy lasers on platforms in space. But more recently, there has been greater emphasis on using ground-based lasers whose beams would be reflected off space-based mirrors. Which of these two approaches now appears to be the more promising, and why?
As a technology, earlier work in chemical lasers had indicated that that might be the most practical at low power levels, to put the laser in space. But it certainly would also be very expensive. And as we made really extraordinary progress in ground-based lasers, primarily this new laser technique called the free electron laser, then it indicated that we should examine that ground-based laser technique very, very carefully.
The free electron laser uses an electron beam, and the technology of particle accelerators to generate laser light. Theory had long suggested this was possible. As a graduate student in the mid-60s, Dr. John Mady, now at Stanford University, was the first to suggest how it could actually be done.
The trick that we used was to force the electron beam into periodic transverse motion by running the beam through an array of periodic magnets. If you imagine a series of dipole magnets that are arranged north-south, 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 in alternating polarity, an electron beam that's run through this array will be deflected first to the right, then to the left, and so on. Each time the electrons are deflected, they emit a little pulse of synchrotron radiation that travels out in the forward direction.
Synchrotron radiation is light. It's amplified by bouncing it off mirrors and recycling it through the magnets until the beam becomes very intense. The wavelength can be tuned to order by changing the distance between the magnets in what American researchers call the wiggler.
Other names have also been described. The French have proposed the word undulator because the beam also undulates as it moves through the field. And the Soviets call these devices snakes or magnetic snakes for obvious reasons.
Bring the gain up a little higher.
At Los Alamos National Laboratory, Dr. Charles Brow.
Shortly after John Mady's exciting results back in the mid-70s, we realized that the real advantage of a free electron laser was not so much its tunability as the fact that it could be developed at extremely high powers. We realized also that we had a lot of accelerator technology here at Los Alamos, together with a lot of laser technology. And you add all those things together, and it was a natural place to do research in high-power free electron lasers.
The main thing to realize is that this is still really an experiment. It's not a settled device, so there's a fairly complicated sequence of turning the system on. Then we have to start tweaking the mirrors and adjusting things. And if we've been running from day to day, within about an hour after we start turning on, we'll have it lasing. And from then on, we start the experiment.
The electrons for the free electron laser are generated here and are then sent to the accelerator, where they are pushed almost to the speed of light. The accelerator consists of a series of vacuum chambers powered by radio frequency, or RF, oscillators. When a negatively charged electron enters the first cavity, it's attracted to the positively charged electrode at the far end. Just as it gets there, the field reverses, and the electron is pushed into the next cavity, and so on. As it's accelerated through the cavities, the electron picks up speed and energy till it's ready to enter the wiggler.
The wiggler has been recently the focus of our research, since it is the device which creates the radiation. And over the last few years, we've been able to take the efficiency of that device, the efficiency for converting electron beam energy into optical radiation, and raise it from about 0.1% to 2%, a factor of 20 improvement.
At Stanford University, researchers have focused on improving the electron beam before it enters the wiggler. These cryogenically cooled dewars house the beam accelerator's RF cavities. The cavities themselves are constructed of niobium, which becomes superconducting when cooled, so the beam is accelerated with minimal energy loss. Another trick to improve overall efficiency is to take the electron beam after it's passed through the wiggler, and instead of throwing it away, bend it with magnets back around and into the accelerator again, where some of its energy is recovered. Dr. Alan Schwetman.
Remember that the superconducting cavities are a very efficient way of converting RF power into electron beam power. Energy recovery permits one to achieve efficiency in converting electron beam power into laser power. The combination of using superconducting cavities and energy recovery makes it possible to build a rather efficient free electron laser system.
A free electron laser converts electricity into laser light. The more efficient this conversion, the more powerful the laser. Here at the Lawrence Livermore National Laboratory, a different and inherently more efficient mechanism is employed to accelerate the electron beam. Induction cells, instead of RF cavities, are used to accelerate the electrons. As the electrons pass through the center of each cell, they receive an energy boost from the cell's pulse generator. The Livermore Group has already achieved very high power from its machine, but plans for even more potent electron beams. Project scientist Lou Eccles.
In this prototype machine, called the experimental test accelerator, we have 8 induction cells giving a total energy of the machine of about 5 million electron volts. In a more advanced machine called the advanced test accelerator, we have 190 accelerating units giving electron energy of 50 million electron volts. The significance for the free electron laser driven by such an accelerator is that the laser light will also come out in very intense pulses. We operate ATA at a frequency of 1 pulse per second by the very nature of how the machine was designed. For a prototype weapon, one must have high average power as well as high peak power. And so our research at Livermore now is taking the form of developing an accelerator that will pulse at a much higher repetition rate.
Research to increase the repetition rate and improve still further the electron beam is done in these tiled pools of Livermore's high-brightness test stand. When the accelerator is operating, the pools are filled with water to shield against radiation. These new magnetic pulse power units can operate at over 1,000 pulses per second, and each one replaces 20 of the current units. The test stand holds components less than half the size of the ATA, yet they should improve electron beam brightness by an order of magnitude.
High brightness refers to the amount of current that is accelerated in the accelerator and how straight it's going, how many electrons are going in the same direction. High brightness is very important for free electron laser application because high efficiency in the wiggler is determined by how bright the electron beam is.
And the wiggler's efficiency determines the intensity of the free electron laser's beam, which in turn determines how much energy can be directed against an attacking missile booster and how much time will be needed to destroy it. Industry is also involved in SDI-funded free electron laser research. This facility at Boeing Aerospace is the first designed to operate at the very short wavelength of about 1 micron in the near infrared, which appears to be optimal for strategic defense applications. Such short wavelengths cause greater damage and permit the use of smaller mirrors in aiming the laser beam. However, since the electric power needed to operate free electron lasers is far greater than can be generated in space at present, they would have to be located on the ground. For their powerful beams to be directed at missiles halfway around the Earth, space-based relay mirrors, probably in geosynchronous orbit, will be required. Each relay mirror must reflect a laser beam to a lower altitude battle mirror that in turn will direct the beam to a target. A critical research concern is the first step, propagating the beam through the atmosphere. This is because the air itself will absorb some beam energy. It will also diffuse the beam, and most importantly, it will distort the otherwise highly coherent laser radiation itself. The wavefront of a laser beam starts out flat, but as it passes through the turbulence of the atmosphere, it begins to distort, developing hills and valleys, the same phenomenon that makes stars twinkle at night. A distorted wave could not be accurately sent on its way by the relay and battle mirrors, so it's crucial that the wavefront that emerges from the atmosphere be flat. A way to achieve this is to measure the distortion across the wavefront 1,000 times a second, then purposely distort the beam as it leaves the laser to compensate for the atmospheric effects. This trick requires a mirror that can be continually and actively deformed. At Adaptive Optics Associates, Dr. Alan Worth.
The standard method for making a deformable element or a deformable mirror is to take a thin sheet of glass and illuminize the surface of it, and underneath put an array of piezoelectric pushers or drivers. And these drivers actually bend the surface of the glass. We're working on a different technology here, and the experiment is right over here. The actual mirror element here is a very, very thin membrane which has been aluminized on its front surface. Beneath that membrane there's a small air gap and then an array of electrodes. The surface of the mirror is caused to deform by applying voltages to these electrodes, voltages that are derived from the signals from the wavefront sensor. And merely the electrostatic, the capacitive forces between the electrodes and the membrane cause the surface of the mirror to deform.
The Air Force Maui Research Facility in Hawaii has already seen several experiments testing these principles of adaptive optics. Low-power lasers have been reflected off sounding rockets and the space shuttle. The distortion by atmospheric turbulence was measured and used to actively adjust the surface of a deformable mirror, which returned the beam to coherence. The dramatic results of tests run in November 1985 are described by the SDIO's Dr. Louis Marquet.
We tracked that target, put the low-power laser beam on it, turned the adaptive optics system on and off, and measured directly on board the detector, with the detector array, directly what the beam was doing, and compared that then with our models of what it should be doing. And the good news is that we really had extremely good agreement with what our predictions were, and as far as I'm concerned, I think it proved the fundamental technical feasibility. Now we have a lot to do in terms of the practical aspects. We have to demonstrate we can do this with a larger aperture. We clearly have to demonstrate we can do it with a much larger than a few watts average power. But the fundamental physics of the issue, I think, have been demonstrating, and we feel that's very encouraging.
It was the promise of directed energy weapons like lasers opening up the boost phase to defensive attack that did much to stimulate the SDI. But now there's also renewed interest in more traditional chemically powered rockets as a boost phase weapon.
Probably the most mature of all of our concepts is to simply put rocket interceptors in some kind of space-based platform. Now, in order to engage in the boost phase, we have to be there when the battle occurs. And that's particularly stressing for kinetic energy projectiles, which do not travel at the speed of light, at much smaller velocities, and therefore they have to essentially be overflying the Soviet Union at the time the battle occurs, or very close to it. There is a great payoff in making those kinetic energy projectiles as fast as possible, but there's a limitation to what chemical rockets can provide us.
The short kill radius of chemically powered rockets, and so the need to have many platforms in place directly over the Soviet launch sites during an attack, means many hundreds of rocket platforms must be orbited to ensure that enough are always in the right place at the right time. But despite this problem, the use of a known technology in a boost phase defense is today receiving increased attention from the SDI, at least to provide a nearer-term defense against present-day Soviet ICBMs. But whatever weapons are used to attack a missile during its boost phase, the first requirement is information about the nature of the attack, in much more detail than present-day early warning satellites provide. Dr. Marquet.
We have to be able to not only know that we're under attack, we have to be able to count the missiles. We would like to be able to discriminate those missiles which might have a large number of reentry vehicles, for example, the SS-18s or 23s, from those that might have only a few missiles, so that we can guide our battle management system and most effectively deploy our interceptors. In addition to this, we need to know some information about the actual track of those missiles, where they are actually headed, so that we can, again, guide our interceptors into a so-called basket and relieve as much as possible the stress on them to make final maneuvers.
September 5th, 1986.
And liftoff of Delta 180 and its SCI payload.
The Delta 180 experiment is launched to study the problems in locating and accurately tracking missiles from space. One problem arises from the fact that the plume of a rocket gets larger as it ascends, until it can eventually become almost 100 miles long and 50 miles wide, and even get ahead of the rocket once there's no air to hold it back. In charge of the Delta 180 project was Lieutenant Colonel Michael Rendine.
The big challenge was thought to be, well, it's going to be extremely difficult to find the hard body, the rocket in this enormous plume. To the extent we can discuss that at this point, it's not nearly as difficult as we thought.
The experiment used a specially constructed third stage, carried to final orbit by the Delta rocket's second stage.
On the top of that second stage, we put all our eyes, all our sensors and our transmitters for those eyes. Then we built a brand new liquid third stage. It's probably the highest performance third stage we've built. On that third stage, we had another sensor. It's the radar seeker out of a Phoenix missile, which is a Navy missile. And we used all these eyes to look at this other stage when we were up in orbit.
The two stages separated. The second stage turned itself around 180 degrees and ignited its liquid fuel engine. It then looked back at its own plume using rear-view mirrors. At a distance of 120 miles, it stopped and looked back at the third stage. The third stage, with its motor off, played the role of a burned-out booster. It was looked at against a background of the warm Earth and cold space, both in darkness and sunlight.
Then we needed to look at some solid motors, and solid motors are different. So while we were over White Sands, New Mexico, we watched an Ares sounding rocket come up. What we normally look for right now is to just detect a vague glow that's good enough for our early warning system. For strategic defense, we need to pinpoint where the rocket is in that plume. So in this experiment, when we launched the Ares, we detected the Ares the instant it lit off.
The small white spot near the bottom crosshair is the rocket as recorded by the sensors. Later, near the center, the rocket's plume can be seen developing.
We did track that Ares from the moment we lit it until the moment the motor burned out. And we are able to detect what we call the hard body, the booster, in that plume. And we detected it with the infrared seeker of a Maverick anti-tank weapon. Now that seeker is a $50,000 seeker. That's a lot of money for us average Americans, but for space hardware, that's extremely inexpensive.
The experiment's data and communication network used 6 aircraft, 38 radars, and 31 satellite links, all tied together by more than 1 million lines of computer code.
In certain regards, the software, all these lines of computer code, although they were necessary for the experiment, were an experiment by themselves. The folks who wrote the code initially didn't think they could do this, at least so quickly. They surprised themselves when they not only accomplished it, but accomplished it very well, and are now just dying to do it again.
The last phase of the experiment simulated an orbital intercept. The 2 stages were ignited, and the third stage, assisted by a small onboard radar, was directed to execute a head-on collision. The second stage sensors were able to follow the third stage plume all the way to the moment it was hit.
And that was the termination, of course, of the mission.
So far, we have discussed some of the most promising weapons and sensors available for boost phase defense. Success here gives a strategic defense system an important edge, because every intercept of a multiple warhead missile like the SS-18 destroys its entire cargo. But some missiles will inevitably escape into the mid-course phase of the attack, deploying not only their warheads, but also a large number of decoys. The mid-course phase lasts perhaps 20 minutes, giving the defense its longest opportunity to destroy the warheads, if only it can find them among all the decoys.
For those missiles that survive the initial boost phase and are able to release their multiple warheads and perhaps decoys, what is currently the most promising technique for discriminating between threatening warheads and decoys?
We will need to eventually have what we call interactive discrimination. That is some way that we can actively reach out and probe the decoys and just measure and really see, is that a real warhead or is it a decoy? And one of the techniques which is promising to be able to do that is a technique that we've made real progress with at the Los Alamos laboratory and supported by other laboratories. And that's what we call a neutral particle beam system.
Overseeing the Los Alamos effort to develop neutral particle beam technology for mid-course discrimination is T.J. Trapp.
Now, the neutral particle beam can very uniquely do that in that it can very easily tell which object is heavy and which object is light. The way it does that is it first off puts a very short pulse of neutral particles on each object. Then that pulse of particles will produce a signal inside the object that depends on how much the object weighs. Now, light objects will give almost no signal, and heavy objects will give a very large signal, so that you can now tell by measuring that signal coming back who is a heavy object and who is a light object.
Here's how it would work. When the beam strikes a low-mass decoy, it passes through it with little interaction. But when the beam strikes a more massive warhead, the warhead gives off gamma rays and neutrons. In effect, it lights up or looks like it's glowing to any space-based sensor able to detect such radiation. A particle beam must operate in space, however, because it can't penetrate the atmosphere, and the beam must be neutral so that it won't be deflected by the Earth's magnetic field. Just such a lightweight, neutral particle beam generator that could be demonstrated in space by the early 1990s is the object of the basic research being pursued at Los Alamos. The beam begins with a source of particles. Here at Los Alamos, they are negatively charged hydrogen atoms. The key element in the particle accelerator is the radio frequency quadrupole, or RFQ. It takes a stream of particles and gathers them into bunches, ready to be injected into the accelerator. Dick Purser.
The great advantage of the RFQ is that it replaces injectors on previous accelerators, which were as much as 2 stories tall, powered by Cockcroft-Waltons, and weighed many thousands of pounds. The RFQ is a vital development in producing systems which are capable of making the transition to space.
The bunches of particles from the RFQ are then sent into the linear accelerator. Before they exit the machine, their electrical charge is stripped off, leaving a highly energetic beam of neutral hydrogen atoms.
Just recently in the accelerator test stand project, the beam coming out of the end of our accelerator here at 5 million volts has been proved to have the full qualities needed to implement the system that our sponsors originally were looking for.
There were several fundamental issues that related to whether or not neutral particle beams could be used for mid-course discrimination. One of them was whether or not enough signal was produced in the objects that you could measure that signal. Experiments have been done to measure what that signal level is, and also calculations to correlate those experiments. And the results of those show that you can indeed get enough signal back that you can measure who is a heavy object and which objects are lightweight or low mass objects in space.
We'll return to SDI, the technical challenge, in a moment.
Delta 180, the SDI experiment.
3, 2, 1, 0, and liftoff. Liftoff of Delta 180 and its SDI payload.
To gather data for design and development of a strategic defense system to protect the United States against the threat of ballistic missiles. The Delta mission, called the most complex command and control space mission ever. Delta 180, the roar of success. We're McDonnell Douglas.
If neutral particle beam techniques prove effective in discriminating between decoys and warheads, then what techniques will come into play to destroy the threatening targets?
We would use rockets. And those rockets could be based in space, and there they would be very small rockets that are similar to the air-to-air rockets that we fire from our airplanes and against other airplanes. They would be small but very, very fast, based in little garages in space, and fire out and home in on the warheads that have been discriminated and designated as real warheads. That way we believe that we could destroy a percentage of the remaining warheads. We wouldn't only use space-based rockets. We have already demonstrated very effectively that we can shoot a rocket from the ground and get it up into position in space so that we can use that kind of system in addition to the other system.
This demonstration began with the launch of a Minuteman ICBM from Vandenberg Air Force Base in June 1984. Minutes later, the homing overlay experiment, known by its acronym HO, continued the exercise with the launch of an interceptor from Kwajalein Missile Range in the Pacific. Guided by an infrared sensor, the interceptor smashed into the simulated warhead, destroying it. Unlike the older, less accurately guided Spartan missiles, which needed nuclear warheads to kill a target, HO demonstrated that direct intercept is now possible. Lockheed Missiles and Space Company, which built the HO interceptor, is now developing an advanced version called ERIS, the Exo-Atmospheric Re-Entry Intercept System, Program Manager William Loomis.
This is the mock-up of the vehicle that we're going to fly. In here in the center we have mostly telemetry equipment, batteries. There are some of the tanks for the propulsion system. On the end here we have a thruster. On this end another thruster, and two thrusters in the middle, which are the provide the maneuvering capability for the vehicle. Probably the most important feature has to do with the infrared seeker and the computer. These are the real brains of the interceptor. They are what allow it to acquire the threatening target, to home in on that target, and to discriminate against any other objects that might be there besides the target, and finally go in and actually kill that threatening target.
Ho opened a 15-foot wide umbrella-like canopy to ensure it would hit its target. Eris will incorporate the same principle, but use a different mechanism to increase its impact area.
Now this vehicle doesn't fly in an axial manner that you would normally think, but actually flies in a broadside manner, in this way to intercept its target, to increase its lethal probability of actually killing the target. Now, in order to enhance the probability of destroying that target, we unfurl a warhead, which is actually up here in this orange box just before impact, which unfurls out on both sides of the vehicle to increase its cross-section again, so that the probability of killing that object is large.
So a successful mid-course defense will need a discrimination system to tell warheads from decoys, then use both space and ground-based non-nuclear interceptors to actually destroy the warheads. Those that escape are now only a couple of minutes from their targets as they re-enter the atmosphere over the United States. These remaining warheads are the responsibility of a terminal defense. Now, speed is of the essence, but at least it's no longer difficult to tell warheads from decoys.
As they hit the upper atmosphere, the decoys, which are very light, would either burn up or get pulled back by the drag of the atmosphere, and just the few remaining warheads would be proceeding on towards the target. And there we would use a more traditional ground-based rocket. We have one in development that we call Head-Eye, and we're making, I think, very significant progress in building that rocket so that we would not have to use a nuclear warhead to intercept a missile.
Head-Eye stands for High Endo-Atmospheric Interceptor, designed for use in the upper atmosphere. Its rocket technology is derived from the earlier Sprint and Spartan interceptors. These earlier interceptors, however, were guided from the ground. This limited their accuracy and required using nuclear warheads to be sure they could destroy their targets. By contrast, Head-Eye will carry its own guidance system, giving it enough accuracy so that a non-nuclear explosive warhead can be used. This, in turn, requires having the ability to maneuver within the atmosphere at very high speed, a capability demonstrated recently in the Flag series of experiments. In charge of the Head-Eye program at McDonnell Douglas, Dean Hoferth.
We have two modes of control for flying the kill vehicle once it's approaching the re-entry vehicle. The shroud has been separated from the kill vehicle itself. The sensor, which is behind a window in the front end of the vehicle, is activated, and we can fly the kill vehicle like an airplane, if you will. And we have thrusters on the back end so that we can establish angle of attack and actually cause the kill vehicle to move by virtue of aerodynamic forces and angle of attack. As we close on the re-entry vehicle itself, where it's important that we get this lateral motion very quickly to close out the miss distance, we have lateral thrusters on board that can actually drive the vehicle laterally through the center of gravity of the vehicle without depending on that aerodynamic force.
Head-Eye, like Eris, will have its own onboard homing system that will come into operation once it has been pre-positioned by a forward acquisition system. Ground-based radar and data processing facilities will be part of that system. They will be aided by airborne sensors flown high above much of the atmosphere. The Airborne Optical Adjunct, the AOA, is being developed as a test bed for these airborne sensors. It is designed to detect infrared radiation and will be carried by a modified Boeing 767. AOA Project Director at Hughes Aerospace, Bernie Skian.
One of the engineering challenges with the AOA sensor is to build a sensor this size and complexity that can fit in an aircraft and also make it lightweight, because there's certainly a weight penalty with anything that goes in an aircraft. This is a casting of the azimuth ring, which the entire telescope sits on. As you can see, this is a very complex form factor. Now, the amazing thing is, for something this large, it can be built rigid enough and strong enough to support the telescope and also be lightweight. This entire huge casting here weighs less than 400 pounds. It's hollow on the inside and has many complex shapes here that have been molded into the contours of the telescope.
In operation, the AOA sensor will collect infrared radiation emitted by incoming warheads. The radiation is then focused onto a focal plane array. This starts the process of actually locating and tracking each re-entering warhead. AOA Chief Systems Engineer Richard Flaw.
In order to detect objects that are outside the atmosphere with the very high background that we have in an AOA system, which is airborne, we have to do two things. First of all, we have to reduce the inherent noise in the detector itself, and we do that by cooling the detector to cryogenic temperatures. In addition, we have to reduce the noise due to the background. One of the ways we do that is to use very small detectors. And as a consequence, we also have a very large number of detectors on the AOA array.
By the time the attacking warheads have entered the atmosphere and begun their fiery descent, the forward acquisition system must have identified them, calculated their impact trajectories, and passed this information on to HEAD-I. Dean Hoferth.
We feel that the HEAD-I program is indeed moving in a direction such that when it's completed, we will have put into the President's decision-making toolbox another capability that he can choose from to select the system that would be deployed to provide that defense for the people of the United States. And the progress that we've made to date in the program indicates that indeed we can demonstrate that capability for his utilization.
As we've seen, an effective strategic defense, a multi-layered system able to intercept warheads in the boost, mid-course, and terminal phases of their flight, will consist of many different sensors and weapons. And that brings up one of the most critical questions concerning the viability of a strategic defense system.
Integration of these diverse techniques and systems into an effective overall system will require command and control, a battle management system. What are you doing in that area?
That is one of the most difficult problems, because this is a system of systems. We're tackling it two ways. One, we have very serious efforts looking at the architecture. How many of what kind of weapons, and what is the communication that are required back and forth between the sensors and the weapons. We're studying that, trying to minimize that, make it as simple as possible. And the fact that we now have such efficient telecommunication systems and such efficient computers offers us, I think, great hope that we can do that. But the way that we'll prove that we can do that is by building a ground simulator of the overall system, so that you can test on the ground in computers how all these systems react and work together. And in order to do that, we have started a project that we call the National Test Bed, which will be out in Colorado, and it will really achieve that effort. Create a place where we will simulate the entire system, and in that simulation gain the confidence that it will do the job that we need.
This is NORAD, the North American Aerospace Defense Command in Cheyenne Mountain, Colorado. The National Test Bed is scheduled for construction nearby at Falcon Air Force Station. The test bed will simulate some NORAD command and control operations, but it will use them together with other simulations based on the new strategic defense technologies. In charge of the National Test Bed, Lieutenant Colonel Richard Paul.
The National Test Bed is a concept in which we can start to test various pieces of technology in a system framework. Weapons technology is being tested in one place. Sensor technology is being tested in another place. Battle management technologies might be tested in a third place. What we want to do in the national test bed is find a vehicle for running those technologies together in a system context rather than individually, and understand what the interactions are between them and how they might work together as a system.
Present simulations are part of the effort to determine the most effective strategic defense architecture, what kinds of weapons might be needed, how many, where they should be deployed. Colonel Paul.
What you see running on the display is a Soviet attack, a hypothetical Soviet attack against the United States. This is an attack of about 100 missiles, but we have put that attack in and put the timing in for that attack so we can look at what the distribution of those missiles are as they fly through space. And we can understand their sequencing, their timing, and that in turn helps us understand how many objects a sensor has to detect, what the bunching of those objects might be as a weapon heads towards those missiles, and just better visualize the whole dynamics of the problem.
Using such simulations, it's possible to test different architectures and assess which ones offer the most cost-effective defense.
We're now getting an idea of some ballpark figures, and some of the kinds of architectures we're looking at for the battle management problem typically include a few sensors up to tens of sensors as a maximum, and several hundred kinetic energy weapon satellites up to a few thousand kinetic energy weapon satellites, each weapon satellite loaded with a few weapons, perhaps any place from 5 to 10 to 15 to 20 weapons.
So far, most of the simulations are unable to mix and match. In other words, they can consider only one weapon system at a time. Working on developing a model called DTEC that could handle combinations of technologies is Dale Henderson.
Well, there exist now, of course, many computer models or simulations of pieces of a strategic defense problem in action, how you might defend the country or parts of it from ICBM attack. Many of these models do many things very well, but there isn't a comprehensive package together which plays all the pieces at one time. For instance, if you'd like to study a free electron laser in cooperation with a nuclear particle beam, in cooperation with homing rockets, how many of each of these do you need to have to optimize your system?
Not only how many, but how would they best be used in combination? Here's the set of chemical rocket platforms we saw earlier. Suppose a few ground-based free electron lasers were also available. How could the lasers and rockets best be combined in a boost phase defense?
Those missiles which had been burning for some time and were about to burn out and to begin deploying their reentry vehicles, you would probably want to assign to a directed energy weapon, because it's a speed of light weapon and could kill that missile even with only 1 to 2 seconds remaining before the reentry vehicles were deployed. On the other hand, a missile just boosting and that still had 2 or 3 minutes of boost time remaining, you might want to assign a kinetic energy weapon to. So you could conserve the fuel on your directed energy weapon and actually hit a missile that your kinetic energy weapon could reach.
This sort of combination implies that a command and control structure must also be included in the planned simulations. Dale Henderson.
Many existing engagement models don't include the uncertainties of command and control, the problems of sending required messages from here to there, the problem with sensors not seeing the right things.
These questions bring us to the heart of the Strategic Defense Initiative, and one question has received a good deal of publicity, namely the difficulty of writing the command and control software for a strategic defense. And it's here that the simulations are beginning to suggest some potential approaches to the problem. Colonel Paul.
We are trying to look now at concepts in which the pieces of the system can be partitioned up so that small partitioned pieces can be designed independently of one another with very tight interfaces defined in between, allowing many people to work on independent pieces of software, but working on pieces of software designed to a standard interface and set of standards, as opposed to writing one huge monolithic software program, and some kind of systems might lend themselves better to that approach.
The supercomputers, now becoming more available, are also seen as helping resolve the software problem. Not only Crays, but new machines based on parallel processing architectures may play an important role here. New developments in chip design and chip materials are also allowing ever more rapid computation. Gallium arsenide is an intrinsically faster medium than silicon for electron flow, as well as being more robust in a space-based environment. And today, the technical difficulties in working with it are rapidly being overcome.
So a possible approach in software is not to try to come up with very sophisticated, optimum performing software routines, but rather some suboptimal routines that are not as fancy, but that take advantage of the high computing power we have available. That is, not to try to finesse a solution by being sophisticated in software, but using simple software solutions and relying on the massive increases in computing power that we expect through hardware, just as we've experienced during the past several years.
The National Test Bed will be an important vehicle to test the overall feasibility of a strategic defense system, and one day to help decide if such a system can be cost-effective.
To summarize our progress overall, I would say we still have a ways to go. We still don't know if the technology is in hand to make a full-scale development decision. But to date, we have not found anything that suggests we can't do it, and we should go along with the promising concepts and pursue those in more detail.
The notable success, however, of some SDI subsystem tests, like the Ho experiment, have encouraged advocates to argue for the deployment of some defensive systems soon.
Recently, there's been growing pressure from Congress for your organization to devote more of its resources and efforts to a nearer-term ballistic missile defense for our strategic missile silos, and to maybe push your longer-range research onto the back burner. What are your reactions to that?
Well, today our fundamental strategy is one of retaliation. And that means that we have to ensure that our offensive missiles are just so well protected in huge, deep silos, or by moving them around in mobile ways, or putting them in submarines, so that we will always have that deterrent there. Now, what SDI is trying to do is to build a defense someday that will make it so difficult that the Soviets would say, I can't achieve my military objective. I can never have confidence that I can get through many layers of defense and either threaten populations or destroy military targets. That's a different kind of deterrence. Now, we're looking at what systems that we could put in place that would help that new strategy, that better strategy, that more stable strategy, as early as possible. Of course, we are looking at that. But it is not the job of SDI merely to enhance terminal defense.
But before any strategic defense can be developed, many key technical questions remain. Among them, the effect of Soviet countermeasures, such as the hardening of their boosters against laser attack. Dr. Marquet.
Until we actually start to carry out experiments with deliberately hardened boosters, taking, again, the idea of putting ourselves into the mind of the Soviet, using Soviet technologies and techniques to harden up those boosters, and then carrying out experiments with hardened boosters to see what the practical limits are. We're really not going to have a good answer and understanding to what the lethality issues are for laser beams. That's one of the critical issues for the viability of the entire directed energy concept in the boost phase. What does it take to actually kill a booster? And what are the penalties for hardening them?
It is in the context of such unanswered but fundamental questions as these that the recent budget cuts in the SDI must be considered.
Congress recently slashed your budget by about a third for fiscal '87. What effect will this have on your current plans and programs?
Well, it has a major impact, obviously. We can't cut a plan which was already, we thought, a prudent plan and an effective plan by a full 30% without having a major impact. In some cases, we've had to take places where we're researching 2 avenues of technology and make a decision that we're just not going to pursue one of those avenues anymore, and we'll go on this one. And in some cases, that decision is quite premature. So that means we're adding risk to the program.
There's no question that the reductions in Congress is going to have a major impact on, number one, the depth of the investigations, the research into which we can go, and also the breadth. If we continue to attempt to resolve these critical issues for a decision in early '92, and I believe it's important not to prolong the issue indefinitely, then we're going to have to give something up. And I'm afraid what will be compromised is the the quality of the data on which we are going to be basing that decision.
One of the most important things for the public to understand about SDI is that it is a research program and that it is not finished yet, and that while we've made a lot of progress, there are still many tough questions that have to be addressed, and we don't know yet if we can solve all of those problems. We're making progress, we're attacking them in what I believe is a logical, structured approach, but we don't have the answer, and we don't know today if we are ready to deploy. So those who think that we are ready for a deployment decision need to understand there is still more research to be done.
Perhaps the most important thing to realize is that a lot of the issues which are now involved in debate about strategic defense, people who are its proponents or its opponents, have strongly held positions this way or that about issues that are really amenable to analysis, and that in some cases that analysis hasn't been done or hasn't been done as well as it might be because the tools don't exist. And the tools should exist. And we look at DTAC as a tool that will enter into many of these central, even political questions. We're not taking sides in it, we're not selling answers, but we are building a tool which can help an honest discussion in place of a more acrimonious debate.
I think we've moved ahead just dramatically. In some cases, the movement is not these very large things where you see a booster destroyed. In some cases, it's something that only a technologist can truly appreciate, and that's where you get a microchip that will be nuclear radiation resistant, and you know how to build it, and build it so it will be low cost. And that's just as important as the big, dramatic kind of visible progress. The way I try to put it is that we're putting the bricks in place one at a time, and they're coming in at an ever-accelerating rate.